We're here to present the Billion Requests Content Recommendation System Challenge. So my name is Elaine Liu. Standing next to me are my colleagues Sinclair Tajay and Akriti Dhasmana. We work for the company called Chartbeat. So Chartbeat is a company that provides analytics solutions for media and publishing companies. We work with a lot of industry leaders, including our next door neighbor, the New York Times. Earlier this year, we acquired a company called Tubular Labs. Tubular is a company specializes in social video intelligence. So Chartbeat and Tubular together, we work with companies in 80 countries, 6 continents, and we track more than 790 billion page views and 100 billion minutes of watch time each year. And I've already mentioned we've had our presence in 6 continents, so that means we're working very hard to crack the Antarctica market. So if you have any local connections there, I don't know, like Penguins Daily, please let us know. We're more than happy to talk to you after the presentation. All right, so we're here today to talk about recommendation system. A lot of the, like the talks in the DS-oriented conference usually is about the algorithm side of things. So today, we're actually gonna walk you through a more, like how do we build a scalable recommendation system from an engineering perspective. We'll first introduce you with our unique and interesting challenges that we're facing for our recommendation system that set us apart from more traditional implementation of a recommendation system in e-commerce or movie recommendation. Then we'll give you a quick overview of how we generate our recommendations. A majority of the presentation today will be actually spent on kind of discussions around architectural consideration, caching strategy, how we use load testing to evaluate performance. Okay, so first thing, challenges. We have identified 4 challenges. First one, constantly changing item space. So our customers together publish more than 10,000 articles on a very busy day in just 1 minute. But in the meantime, 25% of them actually no longer receive meaningful traffic just after 1 hour of being published. That means our system has to adapt to a continuous stream of new articles and expiration of old ones. Second challenge, diverse content dynamics among sites and articles. What do I mean here? So we have time-sensitive articles like news coverage or disaster coverage. We also have evergreen content that were published a long time ago but are consistently generating traffic. We also have old articles that published long before and suddenly become relevant, or we call it resurrect. So in terms of sites, we have sites wanting to promote popular articles to attract a broad audience. We also have sites that want to promote niche articles to keep their loyal readers on the site. So when we build our system, we have to consider all those different perspectives into our design. Third challenge is about the speed and scale requirements of our implementation. So our intended use cases, our API, is to be implemented from the client side as opposed to the server side. So there are multiple reasons for that. For one, some of our customers insist on only implemented our API on the client side. And second, the client implementation actually allows us getting to a lot more visibility into who are viewing and clicking to our recommendation. Third, the client-side implementation allows us to have a lot more control over our own system, right? But it also comes with significant infrastructure undertaking. We need to be able to scale up to 1.3 billion page views a day. And we also need to generate recommendations very fast because, for one, we don't want to slow down the page that our customers need to spend a lot of energy and effort on optimizing. Second, 30% of readers actually spend less than 1 second on an article. So we need to capture readers' attention while they're still at it. Okay, last but not least, sparse user item interaction. This is not an unfamiliar challenge that I've usually faced with the recommendation system, but in our case, it's kind of extreme. So we have 30% of visitors actually visit the site for the first time in the last 30 days, and a majority of readers, like you and me, we don't read a ton of articles every time we visit a site, right? So we actually see 80% article only has less than 3 page views a day. So for each of the challenges I have outlined here, our general approach for each one of them. For the first one, sparse user item interaction, we're going to focus on popularity-based and content-based recommendations, at least for now. For the constantly changing item space, we are gonna we have a batch process, a cron job that runs every few hours to refresh our candidates. For the scale and the speed requirements, we adopted a web queue worker architecture and put a lot of thoughts into our caching strategy. Last one, the dynamic contents among sites and articles. We allow users to customize their recommendations using a variety of API parameters. Now, Arkady and Sinclair are gonna focus a lot more on the architectural considerations and API parameters, including why and how those API parameters actually pose a challenge to our caching strategy and how do we solve that. But for now, I'd like to introduce you to, give you a quick overview of how our recommendations are get generated. Okay, so as I mentioned, we have 2 ways of recommending articles. First one is popularity-based, second content-based, right? But those are not, not the fancy algorithms, and in fact, they're the most common ways to recommending items, but we have added our own flavor to them. So for popularity-based recommendation, we recommend top trending articles, but also incorporating reader behavior. So if you're a reader reading an article on your mobile device, we actually are gonna recommend you top trending articles on mobile because they might be different from trending articles on desktop. We also consider where you are, the region the readers are from, and how do the readers get to the page, whether through search or social, we call it referral. So on the right-hand side is a quick example of our popularity-based recommendation. It's for the site called Snopes.com. Snopes.com is a fact-checking site. There are a lot of interesting content on that site, so I highly recommend you to check it out. So what do we have here? We have something about NFL, Arnold Schwarzenegger, and the shooting in Maine. Okay, so for content-based recommendations, we are gonna recommend articles that are similar to the one the reader is currently reading. We call it target article. In the meantime, we also wanted to consider the engagement metrics of those recommendations. So for example, if an article is very similar to the one that the reader is currently reading, but no longer is generating meaningful traffic, we actually don't want to recommend it because it's no longer relevant to our readers, right? So on the right is an example of the content-based recommendation. Our target article is, does decorative spider webbing pose a danger to wildlife? It's an article on Snopes.com. We choose this metric called weighted average engage time. We also had a filter on the published date. What we have here is something about honeybees, turtle octopus hybrid, carpet python, baby peacock, and a person in bear costume. So we're quite good with generating relevant contents to our target article. And by the way, the UI you're seeing here, like the bottom part, is a Chrome extension that we built on top of our API to allow editorial teams to quickly preview and curate the recommendations. Okay, so how does it work? This is a general diagram of our architecture. You'll see this diagram repeated throughout the presentation. Sinclair and Arkady are going to spend more time talking specific component of the diagram. But for now, all you need to know is a majority of the recommendation generation process happens in the worker. So what I just talked about is the popularity-based recommendation. We have 3 workers to handle that: device, region, and refer, each associated with the reader behavior dimension. And the workflow is simple. We highly rely on our existing real-time tracking system to recommend top trending articles. And as I mentioned, we also consider different reader behavior dimension. For content-based recommendation, we have a separate cron independent of the worker, but still, recommendations are generated in the worker. So let's see how it works. First, let's start with the batch process. It's a cron that runs every few hours to make sure that we refresh our candidates. We get articles metadata, engagements. We also, and then we generate embeddings for each one of those articles using sentence transformer, and we save all those information in Redis. When it comes to actually generating recommendation, we actually generate recommendation after we receive the request. So not before the request, but after. I think a lot of times the traditional implementation of Rexis is actually having the recommendation pre-generated. In our case, because we generate afterwards, we call it online prediction. So we use 3 types of features. The first one is batch feature that we generated in the cron. Second one, online feature, we generate after we receive the request. Usually for newly published articles that we haven't seen before, and we need to generate features for them on the spot. The last one is a real-time feature or real-time metric. It tells us how many people are reading this article right now at this very moment. Okay, how does it work? So we have embeddings for the candidate articles, right? And we have embeddings for the target article. We can easily calculate a similarity score. But we don't end here. We also need to consider the engagement metrics. So we take a balanced view of a similarity score and engagement metrics and get the top performing similar articles. Now, the user can choose to re-rank those articles based on real-time metric, based on how many people are reading the articles at this very moment. And after all this candidate retrieval, scoring, and re-ranking, we are finally able to get our final set of recommendations, and we save that in Redis. Now have a great idea of how the recommendations are generated. Akriti and Sinclair are gonna spend a lot more time on how we serve those recommendations to meet the requirements and challenges I mentioned earlier. Akriti.
Thanks, Elaine. Hi, everyone. So before we get into the architecture itself, I wanted to talk briefly about where the request is coming from. Our customers would be hitting the recommendations engine from the front end of their website. This means that to ensure that the readers of their websites have a seamless experience, we would need to make sure that we return timely and quality responses to the requests. We should also be able to support a large number of requests, since the client-side implementation that Elaine referred to before on our customer's website means that every new page load is essentially a new request. So the 1.3 billion page views translate to 1.3 billion requests. So we previously discussed the process for recommendation generation. Let's now talk about how we ensure quick responses from our system. Let's look in a bit more at our web queue worker architecture. When the request first comes in, it hits our server, and we ask a very important question. That is, have we seen this request before? In this case, let's assume that the answer is no. Now, based on the parameters that were passed in the URL request, we publish a job to the Rabbit queue. We use RabbitMQ here for maintaining our Rex queue. Here, the job spec contains parameters that the worker would need to generate the recommendations. This includes the target article we are generating for the recommendations for, the domain of the customer, as well as other optional parameters like the desired freshness of the recommendations and the number of recommendations. At the same time, we also need to make sure that we are returning a response to our customers. So we make a call to the real-time tracking services to return the top trending articles for that particular host domain as placeholder recommendations. Here, the placeholder recommendations or the trending articles are not really fulfilling the request parameters that were specified by the customers, but they're just something that we return for the time being, while the actual requests are being generated in the worker and stored in the cache store. This means that the next time we receive the same request, we have the recommendations actually satisfying the request. The reason why we do this is to ensure that if our customer is using our response to populate a certain section on their website, we always have something to show there. In the meantime, the worker uses the job spec to generate the recommendations according to the parameters that we specify in the URL params. And again, here when I say URL parameters, it means the number of recommendations, the freshness value, as well as the article that we are generating recommendations for. All of these are used by the worker. Now that we have the recommendations, we also store them in the Redis store, which Sinclair will be talking about in much more detail later on in the presentation. So now that we know that we have seen this request before, let's ask this question again. If we repeat the same request, what happens? Have we seen this request before? Yes. Well, then it's pretty straightforward. We immediately check the Redis store, and we find an instant hit in our Redis store. We return the recommendations right away, giving us an almost instantaneous response. So in this way, our complete web queue worker architecture helps us create a product that can support a large number of requests. I will now pass on the mic to Sinclair for a much deeper dive into the working of our Redis store.
Thank you very much, Akriti. So here's this image again showing our overall architecture. I'm going to focus on this little bit down here. Elaine made this magnifying glass for me. I think it's pretty impressive. So this is what we're talking about, should be clear. This is a really important part of our system. So as Akriti just mentioned, the first time we see a request, so you go to NewYorkTimes.com, you see a very interesting article. The first time you go to that article, the first time anybody goes to that article, we're going to generate recommendations in our workers. But all subsequent visits to that page, recommendations will be served from our cache. So this is our cache down here, which we call the rec store. So the vast majority of requests are getting served directly out of this cache. So it's a very important part of our system. I wanted to talk to you about it today because we got this completely wrong the first time we tried to build it. I'm going to tell you how we got it wrong and how we fixed the problem. So I'm going to start with a high-level overview of how this works, and it works very similarly to any cache. So over here, you've got some computation. I've called it computation 1, and you want to get the result for this computation. The first time you do this, you're not going to have anything in your cache. So you're going to have to do this slow process to get the result for that computation. But once you do this the first time, you can save it back to your cache. And then when you go and ask for the results of this computation again, you can just get it directly from the cache much more quickly. If you have a second computation, it's a different computation. You can't just use that first result. So you have to go generate the result again, save it back to the cache, and look it up again. So this is basics of caching. Maybe some of you have seen this before, maybe some of you haven't. I think there's a very interesting issue here, which I didn't quite appreciate until I tried to start building our recommendation store, which is that computation 1 and computation 2 are different, and you need some way of tracking how they're different. And there's this question almost of the identity of a computation in your cache. How do you match up computation 1 to result 1 and computation 2 to result 2? I'm sorry, this presentation should have had a seizure warning. So there's a very simple strategy that is probably the one that most people use, which is just you consider the inputs to your computation. And if all the inputs are the same, then that is the same computation. I don't know, you can call it the input identity strategy. So this is what we did the first time round, and it led to problems. This is kind of more in detail now, the way that we implemented it. We used Redis. This has come up a couple times in the slides so far, but if you're not familiar with Redis, it's a very fast key value store. It's in memory. And so we're saving all the recommendations we generate into Redis. To pull something out of Redis, you need a key. And so if we're going to adopt this input identity strategy to generate our cache keys, how are we going to do that? We're going to use all the inputs to our recommendation generation to form a key. And so here's an example of a key in our system as we first designed it. And you can see it's very long and terribly ugly, and it's hard to read. And it's actually, I've even cut it off because it just goes on and on and on. This is terrible. I mean, it's just, what is that? The reason it was so long is because our endpoints take a lot of parameters. We wanted to support these as features. We wanted it to be a very flexible API. We're also still figuring out how people will use it, frankly. So we've got lots of options. But because there's so many parameters, if we take this input identity strategy to identifying things in our cache, we have to factor in all these parameters into our keys. And this is just outlining, what all these different things are. So we've got the domain, we've got the path to the article, and then a bunch of different other parameters that do various other things in our API. So not only are the keys very long, but because they're so long, the kind of key space is very large. Each parameter produces, each variation of one parameter produces a different key, so there are lots of different keys. And as a result, we have to be prepared to store things in Redis for all these different keys, and that would require a lot of storage, and this is in memory, so it's going to be very expensive. So this first draft of the Rex store system had all these different problems. So we thought, how do we do better? Can we just strip parameters out of the key? Can we use fewer parameters? And you might be thinking, okay, that seems sensible, but now you have this problem, right? If you just take off all the parameters at the end and only consider the first two, don't you go back to this problem of, okay, maybe we change something way down here in the key, this parameter is now different, but because that's no longer in the key, you can see the first part of the key is the same, so aren't we going to end up maybe accidentally confusing things that we stored in our Redis data store? It turns out that this wasn't that important, and we were able to strip out the parameters at the end, and let me kind of just walk you through why that was. If you think about just taking those first two parameters, it's almost conceptually as if you have this slot that is reserved in our cache for a particular article. And so here is an example of a New York Times article. It maps to this slot because it's got this key, and when we generate recommendations, we cache them in this slot and serve it for future requests. If we have a different article, it gets mapped to a different slot, and we save recommendations there and serve them for future requests. The interesting scenario is, what if we have a request for recommendations for this same article, but with a different parameter, one that is not included in our key under this new system? That will map to the same slot. And I sort of say slot because this then gets overwritten, and we have this idea in our application code of an unsatisfied hit. So this key exists in Redis, but what we store there is not really what we want. And so we do this equality comparison on our recommendations in application code to see if this is really what we want. If it's not, it gets overwritten, and something new is slaved in that slot. And this works because basically we realized that these parameters are not going to change very often on an article-to-article basis. So yes, we're only including the article domain and path in the key, but that is enough because most of the time these parameters will be the same for every single article. If they vary, they will vary article to article, but that's already captured in our key. So sometimes we might overwrite things. We have to support that because that could happen, but it's unlikely to affect the performance of our cache because it happens so rarely. So this worked well for us. It had lots of benefits. The keys are not so terribly ugly. We didn't have to store so much stuff. The performance of our cache was still pretty good. There was some additional application code we had to add, and that increased the complexity of it a little bit, but we figured that was a reasonable trade-off to make. So speaking of performance, I'm going to hand it off to Akriti, who will tell you about how we evaluated the performance of our system overall.
Thank you, Sinclair. Now that we have understood the working of our system in general, we want to be able to evaluate the performance of the engine. As we have specified throughout this presentation, scalability is of utmost importance for our project. We want to be able to handle a large number of requests from our customers really fast. A typical load test for the recommendations engine involves making requests through a web service tool called Vegeta. We make requests at a steady rate while monitoring the performance. At the end of the test, Vegeta gives us the average response latencies, the status codes, and the success ratios of the test requests. So we have established throughout this presentation that there are two important components to our system, namely the web queue worker architecture, which I covered before, and the caching, which Sinclair just discussed. We want to be able to test both of these aspects of our system. So it is now helpful to view a single test run or a single load test in two distinct halves. The first half is when we are making the test request for the first time. Now, if you recall from the architecture overview, earlier in the presentation, we mentioned that the first time we are making a request, the recommendation engine returns the trending articles and submits the job for caching the articles that actually satisfy the request to the worker. So during the load testing, we should be repeating the request to test that the recommendation generation process went through without a glitch, and then repeating the request to verify that we are getting the cached recommendations satisfying the request. This way, both halves of our system can be evaluated. So let's talk first about the rec generation process. When we are making the request for the first time, we would be testing the interaction between the server, queue, and the worker. Essentially testing what happens when the answer to the key question we mentioned before, have we seen this request before, is no. It's a test of the capabilities of our web queue worker architecture. So how do we know that the rec generation process was successful? Well, there are quite a few metrics that we could look at to evaluate this. First up, we have the queue depth of the rabbit queue we are using for getting the recommendation jobs. The queue depth indicates that at any point of time, what is the rate at which the jobs for generating recommendations are being published to the queue from the server. So here, for instance, to the right, we have the chart from Grafana that we use to monitor the queue depth. In general, we would want to make sure that the queue depth is not steadily increasing, because that would indicate that the worker is stuck and the jobs are not being completed. Next up, we have the queue throughput. That is essentially the rate at which the worker is picking up jobs from the queue. This metric is indicative of the health and efficiency of the worker. So at the right, we have the queue throughput. Note that we want the green and the yellow lines here in the graph to always be approximately close to each other for an efficient test run, because that would mean that the jobs are being published to the queue at approximately the same rate as the rate at which they are being picked up by the worker from the queue. And finally, we also need to make sure that the first time that we are making a request, we are getting back the trending articles. So to monitor this, we could look at the status codes for all of our requests. And we want to see 200 response codes throughout our load test, of course, to make sure that the system is working as expected. So we can see that we use metrics such as queue depth, queue throughput, and number of successful responses to make sure that the recommendation generation process went through without a hiccup. Next up, we want to see how our cache is performing. So coming to the second half of the load test, we want to monitor the interaction between the server, worker, and the Redis host. We assume here that each of the requests we made in the first half of the load test should be cached in the Redis store by now. So we should be getting almost instantaneous responses from our engine. In this half of the load test, we primarily look at metrics for the cache store. So first up, we look at the cache hits. These are the number of hits we see when we are looking into the rec store for each request. So we can see that here in green, we have the cache hits. For the second half of the test, we would want to see only cache hits, because we should have each request cached in the store. Another thing we would want to look for is cache misses. So this is the number of times that we did not find satisfying recommendations in the cache store. This is highlighted here in yellow. And during the first half of the test, ideally, we would only see cache misses. And the second half, we should be seeing none of the cache misses. And finally, we also want to keep track of the number of successful job completions in the worker, which means that each job for each request was successfully finished and cached in the rec store. This graph here shows us the number of completions over a given time period. This should increase throughout the test and cut off somewhere as we start the second half of the test. So cache hits, cache misses, and successful completions can all be leveraged to determine the cache performance. Now that we know the metrics, let's look at the performance of our system. So we started off this section by saying that we wanted to see if we could serve really fast responses and handle a large number of requests from our customers. So let's first talk about our ability to handle a large number of requests with caching. In this graph here on the left, we see how our queue throughput was before we implemented caching. We can see that before there was a huge disparity between the rate at which we were publishing the jobs to the queue versus the rate at which they were being picked up by the worker. This changed after we implemented the caching, and we can see on the right that the worker is very efficiently able to keep up with the queue here. And finally, let's see let's see how fast we return responses. So here we have a comparison between the Vegeta output we had from one of our older test runs versus the latest one after implementing the WebQ architecture. So we see here that our request latencies have significantly improved. In particular, we can see the average latency before was around 2 seconds, which we have since brought down just to a few milliseconds. You may also notice that the max latency for the request before was around 27 seconds, which has been brought down to 1 second. The reason why it was so high before was because we were generating recommendations in our server, and sometimes we would get hung up on a single request, leading to a much higher backlog wait time. We have since cut it down because we moved the recommendation generation process to the worker. So again, this is a testament to the changes we have made to incorporate the WebQ worker architecture and the caching in our recommendations engine. I'll now pass on the mic to Sinclair to make a few closing remarks.
Thank you, Akriti. Okay, so why do you care about this system that we built? I think, I'm going to come back to that slide, but basically this architecture worked well for us, so I don't know if any of you in the future may build recommendation systems, but this is something that we thought worked well. We started out with a system that was not very well architected, and as a result, we had a very poor mean latency for our requests. And as Akriti just showed you, we were able to get that down by almost 2 orders of magnitude. I think the huge win here was just moving a lot of the heavy data science recommendation work into these workers, and then being able to serve the vast majority of the requests from the cache. That worked really well as an overall approach, but as you've also heard, there were also some subtleties we had to consider along the way as we built that. It worked really well for us. We had all of these challenges to deal with. I think the biggest ones were probably that we have this long tail of articles that we still want to generate recommendations for, even though they get very few page views. And then we also had to generate the requests very quickly and serve them at a very large scale. I think maybe another takeaway from this is, although of course data science was an important part of it, it kind of like is this little part here, and the rest of it was infrastructure and engineering. So if you want to build a recommendation system at scale, these engineering problems are going to be a big part of it, in addition to the data science. The data science ended up being relatively straightforward for us. Elena is our ML engineer on the team. It's possible she's just really good at her job and it just never came up. But I think there are some inherently hard engineering problems to solve building a system at this scale. Thank you very much.